Okay, so last time we looked at 2.1, right? So we started with the tangent problem. Now, we said that a tangent line should have the same direction as a curve at a point of contact. So I said that for these two examples, right? This line that we have here will be considered as a tangent line because at this point of tangency where they touch, they're moving in the same direction, right? If you zoom in, they're moving in the same direction. I said that this line won't be a tangent because at the point of contact here, there's still some people trying to get in. Okay. So these move in different directions. So that is not what you refer to as a tangent, right? So we made this statement the last time. Now, the thing we're supposed to start with is example one, right? So let's just continue from here. So let's look at what the tangent problem is all about. What is the tangent problem? So we start with example one. And this example is pretty much straightforward. It says, find an equation of the tangent line to the parabola y equal to s squared at the point P11, right? At the point P11. So this is the example that illustrates the tangent problem. Okay. Now, the question I'll pose to you guys is, when you're trying to find the equation of any line, right? Any line for that matter, there are two important ingredients. Can anyone tell me what those are? What do we need to find an equation of a line? What do you need? There are two important things you need to find the equation of any line. You need a slope perfect and a constant close. A slope and a constant close. Come again. You have the slope part, right? Come again. Perfect. A point. So you need the slope and the point. To find the equation of any line, you need the slope and then the point. Now, referring back to the graph you saw here, you realize that at the point of tangency, this point is on the line and on the curve, right? So where they touch, the point is on the line and on the curve. Please, you see that? Are you okay with that? The point here is on the line and on the curve. So that means that if you want to find the equation of this tangent line, we have the point. We have a point. You have a point on the line, already known, right? So in this example, this point P11 will lie on what? Lies on the tangent line and also lies on the curve, right? So in finding the equation of this tangent line, we know the point. We know the point. But the second thing is, we know we need two things. We need a point and a slope. The question is, do you have the slope of this tangent line, right? Do you have the slope? Well, we only have 1 point. And we know from your previous math classes that to find the slope of any line, you can either be given the slope directly or you're given 2 points and then you compute the slope as what? Rise over run, right? You recall that in your previous math class, if you have something like S1, Y1, and then S2, Y2, then you have 2 points. So you can compute the slope, right, of any line as well, say Y2 minus Y1, rise over run. Perhaps I should, let me see if I have space now. Yeah, I have space somewhere here. So you say the slope will be equal to what? Rise over run. So you do, say, Y2 minus Y1 all over X2 minus X1. Or you can do Y1 minus Y2 all over X1 minus X2, right? So you learned this previously. But the thing is, this formula can only be used if you have 2 points, right? And in this problem, you just have 1 point. So that means you are stuck, right? You can't get the slope of this tangent line using the methods that we learned in previous math classes, right? So that is the whole problem. You're trying to find the equation of a tangent line, but we don't have the slope. We can't find the slope, right? So this saying you'll be able to find an equation of a tangent line as soon as you know its slope. And then the difficulty is that we know only 1 point, P, right, on the T, on the tangent, whereas we need 2 points to compute the slope. Please, you see. So that's the whole problem. That's the whole tangent problem. Please, are you okay? Does it make sense? Okay. So the thing is, how do we go about solving this? I need to move on to the next slide. If you need time, please do let me know. You need time copying something from this slide. Also, communicate, right? Yeah, that is true. But that'd be like jumping like about 2.7. I don't know. How many steps? Yeah, that's perfect. That's true. Hunter, that's correct. Yeah, using the derivative, but that's like, you go. So let's build up, right? So, so as I was saying, communicate, right? If I'm speaking too quickly, if I'm writing somewhere you can't see, if there's anything, just let me know. I won't know what's going on at your end unless you let me know, right? So communicate. Let me know. You can unmute yourself and speak. Send me a chat or something. Yeah. I prefer the unmuting part because it's not easy to miss. The chart is easy to miss when they come in, like they come in volumes. Okay, so that's it on the slide. Okay, so we know we are stuck, right? We need 2 points to be able to compute the slope. And then we have only 1 point for the tangent line. So what do? Well, we introduce this idea of secant lines. Secant lines. So what is secant line? Well, just like the tangent line, which comes from Latin, secant line also comes from the Latin word secans, and it means cutting, right? So a secant line is just a line that cuts or intersects a curve more than once. More than once. So the secant line will touch the curve at least 2 points. So you could touch it 2 or more. Now, because the secant line will touch the curve at least 2 points, there will be 2 points. We will be able to identify 2 points on that line, and hence slopes of secant lines can be easily computed. Please, you get that? Secant lines will touch the curve at more than one, like it will touch that 2 or more. So that means that we have at least the 2 points that we need to compute the slope of a secant line, right? Okay, so how is this secant line going to help us? Well, first note that if you have this curve, right, don't forget that the curve that you're looking at is y equal to s squared, right? It's s squared. So that means for any ordered pair on this graph, so this is y equal to s squared, this is a graph. I think you saw this in 126. Kind of like a smiley face kind of thing. Like a big smile down there. Anyways, yeah, so this is it, right? Now, if you want to pick a random point here, say you want to pick any point here. Let's say here is 1, or let me say 2, yeah, 2. Then what will be the corresponding y coordinate? The corresponding y coordinate can be obtained by just plugging the 2 in the s squared, right? So that you get here to be 4. So that means this one is 2, 4. Please, are you okay with that? What about a point here? Say, let's say here is -1. How do you get a corresponding point here? Well, the corresponding point here is just drag this to what? Just plug the -1 in the x, like in place of x. So this will be -1 squared, which will be 1, right? So this point will be what? This point will be -1, 1. Now, for any point on the curve, the ordered pair is just x, s squared. Please, are you okay with that? For any point, you just get the s coordinate. This is the s coordinate. How do you get the y coordinate? You plug it in the curve and then get the y coordinate. Okay. So that means back to the secant lines. So with the secant line idea, what you're going to do is you're going to find the slope of a secant line by letting that secant line pass through the already known point, the point that you're interested in, to finding the tangent. You're interested in finding the tangent at P11, the equation of the slope of the tangent at P11. So you find secant lines that pass through the P11 in any other point on the curve, right? And any other point, right? So that means for this question, one point is P11, and another point is something we call Q, point Q, right? Point Q is what? It's just s, s squared. So this represents any other point on the curve, because the secant line will pass through at least 2 points. So it will pass through P11, and we need it to pass through any other point. And that one, the general representation is what? Is x, s squared. That's the ordered pair. Please, are you okay so far? Any questions? Okay, so what you're saying is this secant line, which is in blue here, the one that you see here, is going to pass through 1, 1, and then Q, a point which you call Q, which is just s, s squared. Please, are you okay? You're going to move on to the next idea. Okay. Now, before we proceed, just know that if two lines have the same slant, if they are slanted in the same way, then they have the same slope. Are you okay with that? If they have the same slant, then they have the same slope. For instance, parallel lines have the same slope, right? So what I'm saying is, recall, the lines with the same slant have the same slope, right? So if you see a line like this, then they have the same steepness. Agreed? Okay, so if you are okay with that, then let's go to this. So I'm going to illustrate what I'm doing here, what you're going to do with this graph, which I was able to obtain from Desmos. So let's see the link. Please, can you see the Desmos plot? Okay, awesome. So let me try and minimize this a bit so that I face the screen. If you can't see, as I said, do let me know. Nice. Okay, cool. So now here on this Desmos graph, right? This is it purple, kind of like close to blue, is the tangent line. You see, it touches the curve, and then there's the curve is S squared, right? And then the green is just passing through this point P. You see, it's on 1. This is 1, 1. This point is 1, 1, right? It's 1, 1. And then you're looking at the secant line passing through 1, 1, and then any other point, right? So this is the S squared, S comma S squared. So what you're going to do is, since we know that the slope, if two lines are slanting in the same direction, they will have the same slope. Let's see what happens. We know we can compute the slope of secant lines. So suppose I have my secant line here. Well, I can compute the slope, right? Observe the slant of the green secant line. Now you realize that as I take like, as I get like ordered pairs, the S coordinate, as the S coordinate moves closer to the 1, then the slant of the green line is kind of like falling on the what? On the purple tangent line. You see? So as I get closer, oh, it's falling. That means that the slopes are getting closer. They are almost the same. You see? So getting closer. At some point, you see that it's almost on it. So that means their slopes are quite close. You see? So that is doing it from the right. And what am I doing? I'm just using ordered pair points that are what? That are getting closer to the X, like the 1, the point here, the point where you're interested in, the tangent slope, right? So get them closer, compute the slopes, and then you can kind of like get an approximation for what the slope of the tangent line is. Now that is doing it from the right. I could also do it from this side. I can compute slopes of secant lines, and as you observe, as I get closer and closer to still this one, from the left, this time from the left, then the slope of the secant line is also getting close to what? The slope of the tangent line, because their slants are almost the same as I get close from the left too. So either from the right or from the left, the slope of the secant lines serve as a good approximation to the what? To the slope of the tangent line. Please, are you okay? Does that make sense? Any questions? Yeah, so that's what we are doing, right? So you're using secant line, secant slopes to try and get the approximation of the tangent slope. Okay. So now let me get back to the PowerPoint. So for now, you're not looking at the exact slope. That's a very good question. Let me go back to this so that you see why you're not looking at the exact slope. Let me go back. Please, can you see the Desmos graph again? I'm sharing that. If you can't see, do let me know. So we are not looking at the exact slope because, see, oh no, it just moved it. Okay, wait. Okay, so you're not looking at the exact slope because, see, if you put it on exactly the 1, 1, the slope is undefined. The slope of this secant line will be undefined because it will revert to the same problem. You will only have 1 point and it won't be a secant line. If you look at the same point, it won't be a secant line. It will be the same tangent line. So it will just be 1 point. And you can't compute the slope of just that 1 point. So it becomes a tangent line when you look at the same line. So they will fall on exactly each other. They will fall on the same line. Like the tangent line and the secant line will fall on the same thing. If you let the secant line be the same point, in which case it's no longer a secant line. Please, you get the idea. So that's why it's an approximation. You can always get it to be close, right? But not exactly the same. Because if it's the same, then it's on the same point. And in that case, it's not a secant line. Any questions on that? Okay. So then let's go back to, I'm sharing the PowerPoint. If you can't see, do let me know. So from the graph, there is justification that we can use the slope of secant lines and get it closer to where you're interested in the point of tangency. And you can kind of get an idea of what the slope of the tangent line will be. So that's the idea. That's what you're going to do, right? Okay. So how do you compute the slope of the secant lines, right? So to compute the slope of secant lines, recall that the point that the secant line passes through is P11, and then what? Any other point, S squared. And here the note is saying that we choose X not equal to 1. Why is that? Because if we choose X equal to 1, then we get K11, which is the same as the P11, and that would be odd. That's the tangent line. It's like the same tangent line problem, you see. we can't get the slope of this line of the slope of this of the point, like these 2 points, using these 2 points. This is the same point. You can't get the slope, right? So we are going to choose any other order pair x, which is not 1, right? And then compute the slope of those secant lines. So I told you that the slope of any line is just the rise over run. So if you have these 2 points, P and Q, right? And then the x is x and then the y is s squared. How do you get the slope? So this is just your x, kind of like s2, y2, right? And this is like your s1, y1. I can change the colors when I'm here. Okay, maybe I can do this. Yeah, I think I can. So this is your, no, let me do it down here. So this is kind of like your s1, y1 point. And then this is your like your, this is your like x2, y2. You see, so if you want to compute the slope, what do? You just do rise over run, right? So that's what you see here. So either you do it as, you are calling it MPQ, right? The P and the Q are the points involved in finding the slope. So that's going to be a rise over run. So the formula is just s squared minus what? So the y2 is s squared, the y1 is 1. And then the x2 is what? Is x. And then the x1 is what? Is 1. So like so. Or you can compute this as what? It's the same as doing 1 minus s squared over 1 minus x, right? But you are sticking with one of the formulas. You are sticking with the first one. Right? So that's what you see here. So that means that any secant line, any secant slope you want to compute, you can just use this formula. Just put in the s coordinate, and then you'll be able to find the slope. Please, are you okay with this? Any questions so far? Okay, so then let's go. So let's try it for 1 point, say 1.5. Recall that you are looking at the slope of the tangent at 1. So you are picking numbers closer and closer from the right and also from the left, right? So 1.5 is quite close to 1, so somewhere here, right? So let's try 1.5. So 1.5, what is going to happen? So just plug it in here to get the slope of that secant line. That would be 1.5 squared. The 2.25 is 1.5 squared, right? Then you just say this 1.5 squared minus what? Minus 1, or 1.5 minus 1. And that's what this is giving you, right? That's how we are getting this, right? And then you calculate this, and then you get what? You get, let me try and manage this. Okay, so you calculate this and you get what? You get 2.5. Please, are you okay? So this will be the slope of the secant line that passes through the P11 and the Q 1.5, 2.25. Okay. Now, we can make a whole list of this computation. As you saw in the sketch, right? I approached the one from the right and then from the left, right? So from the right, so these two tables are representing those computations. So the first one is, you can see that all the S values here are what? Bigger than 1. Right, so that tells you that these values represent from the, these values represent from the what? They represent from the side, right? So something like 2 is say to the right of 1, and then you're approaching. So you take 1.5, they take 1.1, 1.01, 1.001. So for each of these values that they're using, they are getting closer and closer to this number where you're interested in the tangency, right? Now, you can approach from the right, and you also saw that when you approach from the left too, they agree on the same thing, right? So these values, the S values that you're using here, are all smaller than 1. They're all smaller than 1. You see? So that one too is this side. Maybe let me use a different color for that. Maybe blue would be nice. Here, from this side, right? So from this side, right? So what do you see? I see 0. 0 is to the left of 1, somewhere here. And then approaching. So that was 0.5, 0.9, 0.99, 0.999. You can go 0.99999 and so on and so forth, right? Now, what you're interested in is the slope of the secant lines. That's what you're going to use to approximate the slope of the tangent line. Now, at this point in time, all that we're doing is we are guessing, right? We are just guessing. Later on, you learn more like concrete ways of getting these things, right? So let's look at the pattern. When you're choosing numbers bigger than 1, you notice that for the first one, the 2 is quite far from 1. It's far from 1. You're getting the slope of the secant line to be 3. Okay, maybe from the graph, from the diagram, we saw that as we get closer, it becomes better, right? We get better approximation to the slope. So let's try 1.5. What is that giving us? Well, 2.5. Okay, it's kind of like reduced a little from 3. Okay, what we can do better, let's get closer. 1.1. Well, that's 2.1. Okay, it's still falling. Now, 1.01, what is that? That's 2.01. That's the slope of the secant line. Oh, 1.001. Oh, that's 2.001. Huh. That means it's safe to say that if I try like 1.0000001, then it's going to give me something like 2.00001 or some sort. And that is getting closer and closer to 2. You see, it's getting closer to 2. Okay, fair enough. Now let's try from smaller values, like approach from the left, right? You're approaching 1 from the left. So we try 0. 0 is quite far. You are getting 1. We try 0.5. We're getting 1.5. Okay, so it's increasing. The slope of the secant lines are increasing. What about 0.9? 1.9. Oh, 0.99. 1.99. 0.999. 1.999. Oh, maybe that means 0.99999. The closer we get to 1, the slope of the secant lines are becoming something like 1.99999, as many as you can say or rattle up, right? But that one is what? It's approaching what? It's also like 1.999, that a close approximation to this is 2. So either you're using smaller values or you're using big values than 1, right? The closer you get to the 1 from either the right or the left, the closer you are getting to what? To 2. So that means it's safe to say that we can guess and say, the slope of the tangent line is what? Is 2. As I said, at this point in time, it's just a guess. You get more solid ways of doing it, but that's the idea. Please, are you okay on this? Anybody needs time on this? Any questions? Is there any part you don't understand that you want me to go over? So that's the idea. Okay. Okay. So if there are no questions, then let's proceed. Okay, so this is the conclusion, right? The closer this point Q is to P, the closer X is to 1. And it appears from the tables, the closer the slope of the secant line is to 2. So we make the argument that I'm moving to the whiteboard. Oh, does anyone need time? If you need time, do let me know. Okay, so I'm going to be using the whiteboard to, so there's the whiteboard. Sometimes some of the examples are long, they won't fit on the PowerPoint. So then I'll just transfer them here, right? So I'll reference them like this. So this example 1 on 2.1 slice, so that you can see where I'm referring to, right? So here, I guess for the slope of the tangent line is 2, right? So it's 2. Now, when we were trying to find the equation of the tangent line, we realized that this was the only challenge, right? We had the point, but we didn't have the slope. But now that we've been able to kind of like get a guess of what the slope of the tangent is, right, or the tangent line is, then we can just put together the slope and then the point and try and compute the equation of the line, right? So we know the slope. Let's represent that as m. You know this is 2, right? And then the point is what? It's 1, 1. So then we can get the equation of the line. I know you guys have several ways of finding this, but we will mainly be using the two ways, right? So we can either use, at this point, it's up to you, right? You can choose which one you want. You can either use slope intercept form to find this. So let's find the equation of the tangent line. So with that one, you have y equal to what? Mx plus b, right? So you know the m is 2, right? That's the slope of this line, right? Let me add the line here, right? You know the m is 2. So let's try and solve for b so that you get the equation of the line. So you can do y equal to 2x plus b. Now to make this equation complete, we need to solve for the b. How do you solve for the b? We know that P11 is on the line. is on the tangent line. So you're just going to solve this as follows. So you do like y equal to, so that'll be okay. I think I see a question, but let me finish with the equation, right? I'll come back to the question. So that means that this one, x is 1, y is 1, right? The P11 means when x is 1, the y coordinate is 1. So you just put that here, 1 equal to 2 times 1 plus b. So that gives you 1 minus 2 equal to b. Hence, b equal to -1, right? So that means your equation of the tangent is y equal to 2x minus 1. That's your answer. Okay, so I have a question. Why is the slope of the tangent line 2 if the slope equation equal to 0.5? The slope equation equal to 0.5. Oh, okay, I see what you mean. Please, anybody needs time here. I'll need to go to the PowerPoint to try and explain this. Let me wait a second. Oh, I'll be posting these files too on the under the file session, what I showed you the last time. I'll be posting everything. Okay, anybody needs time here? I'll still come back here though. So let me try and explain what's happening. Please, I'm sharing the PowerPoint now. If you can't see, do let me know. So I think this is what you are referring to, right? The 2.5. So this 2.5, with this 2.5 answer, I was just illustrating how you are computing the slope of the secant lines, right? I said that the general formula for the slope of secant line is what? MPQ, that's the what you're using to represent the slope of the secant line, passing through the point P and Q. And I said it's s squared minus 1 over s minus 1, right? And this was just an example. I was saying that when the x is 1.5, the corresponding y coordinate would be 2.25, because this 2.25 is what? It's just 1.5 squared. That's what I put here, right? So this was just an example. When the point is, like the secant line passes through P11 and 1.5, 2.25, right? So that one you get 2.5. And this table here is just illustrating. You see that the 1.5 is just part of it. So for each of these x's, they computed the secant slopes using this formula, right? So you're not using this per se. You're not using 2.5 because now we know that there are some values when we go closer to the 1, which were smaller than 2.5. They were smaller than 2.5. So you will not be justified in saying that this is going to be 2.5, right? Because we observe smaller numbers. We have 2.1, 2.01, 2.001. And we can even envision that as we get closer, like 1.0001, this is going to even be smaller than that 2.01. It's going to be like 2.0001 of some sort. So the closest approximation we can argue, or as our guess, is what is 2, right? And then this is also like verified from this side. From this side, you see the numbers are getting close, right? As you get closer to the 1, this is also like 1.999. So we can envision that, yeah. So I see you understand, yeah. So 0.9999, that's like 1.999, and the 2 are agreeing on like 2. That's why we use 2 as our guess. Okay. Please, any other questions on this? Okay. So let me go back to the whiteboard. So I was showing you, after you get the slope of the, okay, wait. When do you homework? Will we be able to use decimals? No. For home, no, wait. For homeworks, right, you can use decimals. Feel free to use the technology, right? Unless maybe the question is about graphing, that you have steps provided to you. Otherwise, you can use decimals, yeah. I even have, for homework 3, I even have a decimals thing that I'll show you to help you solve it, right? I'll show you that one later on. Yeah, so that one, feel free. But for quizzes, no calculators, no decimals, no notes, nothing, right? So that's the difference. Okay, so now I was here, right? Yeah, you're welcome. So I was here. So what I was saying is, after you find the slope of the tangent line, you guess it, right? You can just compute the equation of the line by, we are going to stick with 2 ways, slope intercept form, which is this. And then, or you can also use the point slope formula. Feel free to use any other ones, but these are the ones that I'm just going to talk about. Point slope formula. It's all on you, whatever you want to use, as well as it's fine. Yeah, you can use it. So for point slope formula, you have to remember the rule, right? The point slope formula goes as, you have to do y minus y1 equal to the slope x minus x1, right? So that's the point slope formula. Okay, so here, the slope is what? Our slope is equal to 2. That's our guess. And then our point is 1, 1. So that will represent our x1 and y1. Please, are you okay so far? Any questions? Okay, so I'll need to move on to the next slide. Do let me know if you need time to copy this. Okay. So after we found the slope and then we have the point, we can just compute the slope as what? So y minus what? Y1 is 1. M, we said our guess is 2, and then x minus 1. So let's solve this. We have, oh, okay, your computer, okay, you're fine. I think it's time I took the attendance anyway. Let me finish this and then I'll take attendance. So with this one, on your homework, right, unless it says simplify, you don't have to simplify. So if on exam you write this for me, I'll give you the full points, right? But let me illustrate that you are getting the same answers either way. So let me follow through and solve this. So distribute the 2, you get 2x minus 2 and then plus 1. And that's to give you y equal to 2x minus 1. The same thing, right? As what you had here. So either slope intercept form or point slope formula, you're good, right? Choose whichever works for you. Please, any questions on how to find the equation of the tangent line? Okay, so now let me take attendance. It's already 30 minutes in. Mark all present. Okay, I have it now. Done. Okay, so back on the PowerPoint. So this is just talking about what we said, right? So this suggests the slope of the tangent line should be 2, right? Now, this is a very important conclusion. We say that the slope of the tangent line is the limit of the slopes of secant lines. You see, the slope of the tangent line is the limiting value of the slope of secant lines. And this can be expressed symbolically as follows. So you can write this. So something like LIM representing limit, and then the Q is approaching the P, right? The Q is the point. Don't forget the Q is x comma s squared. Do you remember? This is the point that the second point that the secant line passes through, apart from P, right? So as the Q point gets closer to the P, right, because the P point is here, and then the Q point could approach from here or from this side. So as it approaches the P, so that's the limit, right? Then the slope of the secant line becomes what? The slope of the tangent line. In other words, we can write it as follows. LIM, so the limit as s approaches 1 of this, the s squared minus 1, this is the slope of the secant lines. Right, that's what the formula used for the slope secant line, equal to 2. That's all. So this notation will come in handy in 2.2. Please, any questions on the tangent problem? Okay. Anybody needs time here? Okay. Then let's go. So here directly, they just give us the equation, right? But I showed you how to solve them. So either this or this, either one will be acceptable. Okay, so now this graph just illustrates what's happening. The one that I showed you on Desmos, right? On Desmos. So you can see the tangent line as your T, and then the secant line is your blue, right? So as we get closer, this is the point P11, right? P11. And then as we get closer to this, the secant line is falling close to what? To the tangent line. You see it's decreasing as we get closer and closer. So here the X point is somewhere here. Here the S point is closer, right? It's getting closer to the 1. So as you get closer to the 1, the slope of the secant line is getting closer to the slope of the tangent line. Now this one is from the right. That means that there are bigger values than 1, right? So this is the limiting process. From the left, you can choose smaller values, right? From the left of 1. That one too, you see the secant slope, the secant line is a blue, right? And the slope, as you get closer to this point, right, then it's also getting closer and closer. Like it's like, so the tangent line is like so you're getting closer, it's falling onto this. So that's what an approximating value of the tangent slope, right? So this is from the left. So you have to do from the two sides. Okay. I think I see 1 sec. Is that about a PowerPoint or something? Or you're good? Okay. Okay, nice. Anybody needs time on this? I already illustrated this using the Desmos, and I think that one's much more nicer That one, you see it in motion. So, okay. Now, one thing is, in science in science, right? Most of the time, unlike the problem that we had earlier on, for that one, we had y equal to s squared. We had an explicit solution for y. We had y equal to s squared. We can actually plug in any x we want. You see, we can plug in like the 1.01. We can put in 1.001. We can put in 1.0000001. Any number we feel like, right? We can try and make it closer and closer as we want. But life is not always that simple. And sometimes when you're working on stuff, you are dealing with experimental data and not a formula, right? So I'm going to explain what this one is about. So what if you're giving experimental data? For that one, you're just giving points. Let's say you perform an experiment in the lab and then you are able to record points, not a function, right? It's not a function, it's just a point. Like when it's 2, this is 500. When it's 1, this is 1,000, and so on and so forth. What if you're giving like an experimental data? How do you estimate the slope of a tangent line when you have such a function? So that's what you're going to look at now. So here I'm going to show you 2 ways of doing this to estimate, right? So we look at example 2. So we have a tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour, right? The values in the table show the volume V of tank remaining in the V of water remaining in the tank in gallons after 2 minutes, right? So when the time is 5, in 5 minutes, you have this remaining. And 10 is what? 444, and so on and so forth, right? And then you have nothing remaining at time 30, right? It's just 0. Okay. Now, if P is the point 15 and 250, right? So 15, 250, so 15 minutes, and then we are left with what? 250. So there's this point. On the graph, find the slope of the secant lines PQ, when Q is the point on the graph at time 5, 10, 20, 25, and 30, right? So for this one, we are not giving an explicit function. We are giving like data points. So how do you do it? For the first part, A, you compute this as follows. So A, this one I have space here. So at T equal to 5, what do we have? We just have to going to find the points involved. The points are PQ, right? It's P and Q. So the P is always the same. It's 15, 250. P 15, 250. And then Q is what? When the T is 5, the Q is going to be what? So just locate the V. Sorry. Yeah, the Q will be 5,694. Right? So that'll be 5,694. Now we have 2 points, so we can compute the slope of the secant line as follows. So let's call it MPQ, so that it's consistent with what we did earlier on. So that'll be just what? The rise over run. So you can either do 250 minus 694 over, where did I start from? I started from the top, so I have to do 15 minus 5. You can either do this or you can do 694 minus 250 over 5 minus 15. Yeah. Can anyone please help us with this? Please, let's see what you're getting for this. Try some math here. And then I write when T equal to what? Now let's look at the other one. When T equal to 10, right? Then the point is still 15 to 50, right? And then what are the points involved? What is the Q? The Q will be 10, what? That'll be this point, 444. 444. Right? So let's compute the slope of the secant line at this point. So that just be equal to what? Can go so 250 minus 444 over 15 minus 10. Right? And that also give you something. So please help me out with this. Either one is fine. Like whatever you get, please help me fill this in. So what about 1T is, the next one is 20, right? So 20. The points involved are P 15, no, not 15. No, yeah, 15 is still the same. That one, the P is the same point. And then the Q is 20, and then that'll be this point, right? So 111. So 111, right? So our slope of secant line will just be 250 minus 123. Okay, let me do this way. All over what? 15 minus 20, right? And we get an answer to this too. Oh boy, let me just put it here. And you get something here. Please help me with these computations. If you get any, just let me know and I'll put them in. And then at t equal to, what do you call it? The next one is 25, right? So for 25, what do we have? You're going to have the point P, which is 15, 250. And then the Q is 25, 28, right? So the secant slope will be completed as what? As 250 minus 28 over 15 minus 25. And then you get an answer to this one too. And then the last point is when t equal to 30, right? When t equal to 30. So for that one, the volume at that time is 0, right? So there's nothing in there. So you have P 15, 250, and then Q, and then 30, 0, right? So you can compute the slope of the secant line as what? So rise over run. So 250 minus 0 over 15 minus 30. And you can get this too, right? Has anyone gotten any of these? If you have any of them, let me know. Or you want me to grab my stuff? Oh, okay, nice. I have someone coming. So first one is 444 over negative 10. Yeah. So what do we get for that one? Negative. Nice. Thank you. And as I said, feel free to speak your mind, right? You're all learning, so it's okay. Make your mistakes and learn from them in this class. Yeah. So this is it. And then the next one, anybody with any solution is fine. Any solution will be welcome. No. Okay. Let me help. I think, okay, for the first, oh, okay. I'm getting 2 different answers for the first one. Maybe let me help in. Let me help with this. So since I'm getting 2 different answers, but please help me on the others. If you agree on some of them, then we can just write it there. So that'll be 694 minus 250. And then that's negative 10, right? So for that one, you're getting negative 4. Okay. So that's an error. Let me give me a sec. Okay, so what's this one? Design. Thought you could just select something here. Okay, either way. Function F5. Okay, t equal to 10. I think I'm getting the answers here. Okay, so you agree on a t equal to 10, right? Okay, so let me see. We are here. T equal to 10. Okay, so that one you got negative 38.8. Okay. Let me just do this. So whenever in class you see something like this, it's a proposed answer, right? In case you see something like it's proposed. If I make a solid rectangle around it, then it's a final answer, right? So just note that. So this, I would just say it's proposed because there could be maybe a mistake or something. So what about this one? This negative 44.4. That's what I got. Is that what you got? The charts are negative 44.5. Huh. Okay, so let me do this. I got that too. Oh, okay, cool. So let me just do this so that at least we can conclude on this. So this is this. Like you see a rectangle around, that's a final answer. And then for the 10, that'll be, what is that? 250. Nice. You got that too. Okay. So 250, this is good practice, right? You get a similar thing on your homework. And then 15 minus 10. Or t equal to 10. Okay, so that one is, yeah, that one is perfect. I got the same thing, right? And then for this one, we have 250 minus 111, 15 minus 20. And that's also negative 27.8. And then the other one is 250 minus 28 over 15 minus 25. And then that's also negative 222.2, final. And then this one is 250 over 15 minus 30. Are we out of time? Let me check.
You have 4 minutes left. Nice.
Thank you. Okay, so negative 16, but I've taken attendance. So yeah, I think this is just what I have to do. Okay, 16.6867, right? So 0.68, so something like this. right? So with a bar on top, that means it repeats. So something like this, yeah. So we are here. Please, are you okay so far? Now, we are interested in the slope of the tangent at what? At 15 to 50, right? This point. So we computed all this. So B, estimate the slope of the tangent line at P by averaging the adjacent slope. So this is the first technique. One technique is if you have experimental data like that, right? Or in fact, even if you have continuous function, what you can do is you can just average the adjacent secant slopes, right? So that's what this one is saying. Estimate the slope of the tangent line by averaging or the two adjacent secant lines. That means that you pick the secant line from here and then from here, the one that you obtain from here and then from here, and then average them. Those are the closest. So find the average. So just sum them and divide by the total number. That's 2. Right? So that's the first technique. So for B, average of adjacent secant slopes. I think I see something in the chat. Give me a sec. Yeah, negative. Oh, okay. Perfect. Page, thank you. So that means in this case, you are going to estimate and say this is, what do you have? What are the adjacent secant slopes? So those will be at time where? 10 and then 20. So what was that? So at time 10, we had negative 38.8, right? So that would be negative 38.8 plus, what's the other one? At 20, that one was what? Negative 27.8, negative 27.8, right? So plus negative 27, negative 27.8. So average these two, right? Can anyone please help me with that? Anyone got that one? Or because of time, sometimes I may have to come in and do these things. Okay, negative 38.8 minus 27.8, all divided by 2. So that's negative 33.3. Are you okay with that? So that's final. So that's how you get it. So this will be an estimate of what? Of our slope of tangent line at that point 15, at that point 15, at time 15, right? So the average of adjacent secant slopes. On exam, I don't care. It doesn't matter because you're not using a calculator, so I won't mind whether you use fractions or decimals. In fact, I'll even advise against using decimals. Don't simplify unless you're asked to. Yeah. My writing will all be on it. Okay, and I'll post everything. Please, anybody needs time here? My time is almost up. Just a couple of seconds. Okay, so the other part is if you have an estimate of what the slope is, right? 11:49. Okay. Let me, because I can't finish this point when I start. So let me just end here. Right. So that'll be it for today. We continue. We continue when? Yeah, we continue on Friday. Yeah. So see you then. Yeah. So that's all. Thank you for your time.
Bye. Thank you.
You're welcome.
Thank you.
Thank you.